Okay, this is going to be a comprehensive summary of the life table, which is a subsection of the topic of contingencies in actuarial mathematics. And this is going to be everything that you need to know from the subsection in order to write the exam. Now, obviously, this is not sufficient alone. You should also go and attempt questions by yourself and make sure that you actually are understanding everything that I'm going through here. Okay, so there's two formulae that are going to be pretty important and are going to come up very regularly, or two symbols at least, and that's TQX and TPX. Now, TQX represents the probability that a life now aged X dies within the next T years. And a formula for this is the integral from 0 to T of SPX, which comes from here, times by mu x plus s ds. Okay, so what I'm essentially saying with this is, maybe I'll first explain what SPX is and mu x plus s is, and then we can go and understand that. Okay, so TPX is the probability that a life now aged X lives for the next T years. So it's still alive after T years. So it's still alive at age X plus T. Okay, so this is when he dies within the next T years, and this must be he doesn't die. So he lives until the end of T years. Okay, so this now intuitively means the probability that a life aged X survives to any time point S, and I'm going to slide that time S from 0 to T. At any time point S, he's going to be alive, and then mu x plus s is the force of mortality, or the rate of mortality, and rather not rate. Rate, typically in questions, when they refer to rate of mortality, they're referring to the probability of mortality, and it can be a bit ambiguous, so I'll reserve force of mortality for this symbol. Okay, so force of mortality basically means at an instantaneous time point, an infinitesimal time interval, the probability that this person is going to die. So you can interpret h times by mu x plus h as, or just as h times by mu x as the probability that a life aged X will die over the short time interval from X to X plus h. Okay, so this here we'll interpret as the probability that they die within this time interval. So mu x plus s as this force of mortality is not actually interpretable as a probability. Okay, so what we do here is we take the probability that this life survives to time s and multiply it by the force that it transitions out from being alive to being dead at time x plus s, or rather at time s, which is age x plus s. And then if we integrate that over all possible time points between time 0 and t, we'll get the probability that they die at any of those points. So intuitively, they must live to a certain point, and then they can only die once. So they die at that point, and I must take into account this person being able to die at any point between 0 and t, which is why I integrate. So they can die at any point, which means it's a continuous sum. Okay, then TPX as the probability that a life aged X survives until time t. The formula is going to be the exponent of negative integral 0 to t mu x plus s ds. Alright, now this has a slightly more complicated understanding, and I don't think it's worth going through right now, but you definitely should remember this formula. Okay, the understanding, the reason why I don't want to go through it is because it comes from proof that's somewhat related to, or that is related to, the exponential distribution. And so you can imagine that an understanding would take quite a long time to go through. Okay, so now another thing that's important for you to understand is the difference between ultimate versus select mortality. Okay, so ultimate mortality is mortality that varies only depending on the age of the policyholder. Select mortality is mortality that varies depending on age plus, maybe not plus, but age and duration. Duration since a specific event. Okay, so ultimate mortality, age, how do we interpret this? This just means that as someone progresses in life and becomes older, their force of mortality is going to change. So someone who's very old might have a higher force of mortality than someone who is young, because of all the health aspects that go to it, and because humans are thought to not be able to live for an infinite amount of time. So as you progress and as you become older, you become more likely to die. Okay, and then select mortality is also saying that it's not just age that's going to affect this person's mortality, it's also going to be the duration since some specific event. And generally this specific event that we're going to be talking about is since policy inception. So since the policy holder takes out his policy with the insurance company. Now, why do we do this? Well, we do this because the insurance company is looking to distribute policies to people who have favorable mortality rates. And so people, in order to get a policy with an insurance company, have to be in relatively good health. Okay, generally speaking. Then after that point, as time progresses, we can expect this person to converge to a normal person's level of health. And so after a certain period of time, we'll stop taking into account this duration since policy inception. But within a particular period of time, say 2 years, that's called a select period, where we do also take into account duration, what we are actually saying is that this person has mortality, let's say they're 50 years old and they took out a policy 1 year ago. So they took out the policy when they were 49. This 50-year-old, his mortality is different to someone who's 50 but doesn't have a policy, or who took out their policy 10 years ago. Okay, so that's generally the difference between ultimate and select mortality. And the way that we denote this is, if I just look at this probability of survival, I'll say TP, and then I'll have the age in square brackets there for select mortality, and then ultimate, the same thing would just be TPX. And then let's say this person from select mortality had survived already a year, so it was a year since the policy inception. So that would be X plus 1, and then I'd say like T minus 1 in order to get the remaining years in this T. Okay, so eventually, once this person gets to the end of the select period, so let's say the select period is 3 years, then this will be Tx plus 3 would just be equal to the probability of x plus 3 for t minus 3. And that's because from 3 years onwards, the mortality no longer differs. So once this person is already aged x plus 3 and they were aged x at policy inception, there's no difference in mortality. So I'm going to make these equal, the ultimate and select mortalities. Okay, now another concept that's important is the principle of consistency. Okay, now what do I mean by this? I mean t plus s px is equal to tpx spx plus t. I'm going to explain this in a moment. Is equal to spx tpx plus s. So I have someone, this is a timeline, someone currently aged x, and then I want to see at age x plus s plus t. This is the probability that someone aged x survives all the way to that point. This here, which is obviously equal to those two. Okay, now let's put age over there, and I'll put time over here. So this is time point 0 when they're aged x, and this is time point t plus s when they're aged x plus s plus t. Okay, then what this is saying is at age x plus t, or at time t, this person must survive to that point And then, once they're aged x plus t, they must survive another s years in order to get to s plus t. So the product of those two probabilities is just equal to the probability that he survives that entire time period. And this can similarly be described with this. So now instead of doing t years first, we first do s years. So the person survives until age x plus s, and then from there survives from age x plus s to age x plus s plus t, which is an extra t years from time s. Okay, so that's the principle of consistency. The principle of consistency is basically saying that the time intervals will be independent. So once someone has already survived a certain point, up until a certain point, beyond that point, I can say, I'm not going to take into account the fact that he's already survived. So I can just make these as independent events and multiply them. Okay, now another formula for TPX is going to be equal to LX plus T divided by LX. So what this means is the number of people that are alive at aged X plus T divided by the number of people that were alive at age X. Okay, so that makes sense, generally speaking. Now, the only problem with this is with respect to what population am I talking about? If I'm saying the number of people that are alive, it seems rather arbitrary if someone's in different countries now or have the same mortality but is on different places. How am I talking about number of people that are alive? So instead of talking about a specific population, I'm going to have a reference number of people, and I'm going to call that L alpha, which is going to be the radix. Now the radix is the number of lives that are starting out aged alpha in a homogeneous population, or homogeneous population. So what that means when I say homogeneous population, that is a population that all has the same mortality, is assumed to have the same mortality, or mortality that's similar enough for us to not differentiate between them. Okay, so L alpha is going to be the radix. This is the number of people that will be alive at age alpha that we're going to assume from that point. Then using probabilities and mortality and how the mortality of this population is actually defined, the behavior of that mortality, we can then calculate the other populations at different ages. Okay, so in order to get Lx, then we would say Lx is equal to L alpha times by x minus alpha p alpha. Okay, so if you don't believe me, then I'll just quickly expand this. So this is L alpha, and then this here will be L alpha plus x minus alpha divided by L alpha. So those two will cancel, and those alphas will cancel, and the right hand side will just be equal to Lx. Okay. Now, we also have L omega, which we're going to call equal to 0. So omega is going to be the maximum possible lifetime that someone can live to. So we're expecting now for this population 0 people to be alive at that point, because if anyone does live until that point, we're just going to say that they die at that point. Okay, so we have a theoretical maximum age. Now, there is not necessarily a theoretical maximum age. So typically omega is equal to infinity, but we generally don't see people living past, say, 125, 120. So oftentimes you'll find omega to be a number that's similar to that, or even smaller, just because so few people actually make it beyond that point. So it's pointless extending your life table beyond that for no one who's going to arrive there. And anyways, we don't have enough data to properly create a life table that can model mortality beyond that point, because there's so few people who actually make it beyond there. Okay, now the way that we're actually going to define Lx is going to be the expected number of lives, and then I'm not going to write the rest of it, the number of lives who survive to age X. So it's, take careful note, it's the expected number of lives, not just the number of lives, because number of lives refers to there being a specific population. But as I explained with this radix, we're not actually referring to a population. It's just in order to have a reference category, we have to have this radix. And so there's no set population number. We just look interested in one individual, and we're using theoretical numbers in a population in order to define that. So it doesn't actually matter if you had your radix to be 0.5 or 500,000 or 200,000. It really doesn't matter, because what's important is the number of people that are alive at different ages relatively to each other, okay? Not the actual number. So alone, this number doesn't mean anything to us, which is why we use an expected number of lives, and we're only interested in them relative to each other. So a ratio of them, which gives us the probabilities of survival. Okay, now another thing that you'll have to know is Tx, which is the complete future lifetime of a life aged X. Okay, so let me write that. Okay, so this basically means if someone is now currently aged X, then they have Tx number of years left in them, and then they're going to die at time now plus Tx. Okay, that's basically what we're saying. So this has a probability density function, which means that this is actually a random variable. So we don't actually know how much time someone has left in them. So we're going to give this some type of probability density function. So this random variable will take on certain values with certain probabilities. So I could expect someone to live over 100 years with a certain probability, or less than 100 years with a certain probability. And so I have a PDF for this, which is going to be equal to TPX times by mu x plus t. Okay, now as you remember, our formula for TQX was equal to the integral from 0 to t of SPX mu x plus s ds. So what I've essentially done here is I've integrated this PDF I must change this variable ds. I've integrated this PDF from 0 to t. So what happens when you integrate a PDF? Well, you're going to get the CDF at that particular point. So this is going to be ftx at time t. Okay, or the probability that tx is less than or equal to t. And we can interpret this. This is the probability that the complete future lifetime of a life-aged x is less than or equal to t. Okay, which makes sense because we want the probability that this person aged x dies within the next t years, which is exactly the same interpretation as I've just said. Okay, from here. Okay, so we know that that's true. All right, now we also have the expectation of tx. So what happens if we want to know how long this person that is currently aged x is expected to live? Well, we integrate from 0 to infinity if I assume that this person could theoretically live up until any age. So 0 to infinity. And obviously, they can't live in a negative number of years. They have to, their lifetime lies ahead of them. Okay, so 0 to infinity. And my variable here is going to be t. So it's t times by the PDF. The PDF is tpx mu x plus t dt. And then if you do integration by parts, you come to the integral from 0 to infinity tpx dt, which equals to this symbol here, which we're going to use for the complete expectation of future lifetime. So the complete future expectation. Okay. Now we also have kx, which is the curtate future lifetime of a life now aged X. Okay, and this is going to be equal to the floor of the complete future lifetime. Okay, so what I mean by that is if someone, their complete future lifetime is 2.5 years, then the curtate future lifetime is going to be 2 years. So it's the floor of 2.5. So I just cut off that decimal. Okay, so I'm looking at the number of whole years of life that they have left. Okay, so if I want to compare QX and mu X, I want to know which one's greater. What I have to know is whether the probability density function of the complete future lifetime of a life aged X is increasing or decreasing. So I'll explain to you what I mean. Let's say this is the PDF. So this is TPX mu X plus T. This is my T axis. And this is time 0 and this is time 1. Okay, so what do I have time 0 and time 1 here? Okay, well, at time 0, the life will be aged X. And I'm interested in QX, which is the probability that a life aged X dies within the next year. So there's an implicit 1 that's hidden over here. So if this number that precedes the Q or the P is 1, then you don't have to write it. So obviously, if it's 0.5, 20 or whatever, if the number here is not 1, you still have to write it. But only if it's 1, you don't have to write it. Okay, that also applies to PX. Okay, so I have a probability density function, and I'm interested in this interval 0 to 1 because I want to know the probability that this person dies between the age 0 and 1. So this equals to the integral from 0 to 1 of this probability density function. Okay, now how am I going to compare this to mu X plus T? Okay, well, there's a useful trick I can take advantage of. So if I drew this constant line down here, at this particular point, I have 0 px mu x plus 0. Now 0 px is the probability that a life aged X survives the next 0 years. Well, if he's alive right now, he's already done that. So this happens with probability 1. Okay, and then that 0 can fall away. So this just equals to mu x. Okay, so this constant line over here is mu x. Okay, now this, we can see if I'm integrating this PDF from 0 to 1, if it's increasing, it moves above this mu x line. Okay, and if it's moving above that line and integrals represent area from 0 to 1, then this integral will represent that area, which is greater than the integral just of 0 to 1 of mu x, which dt, okay, that's horrible, let's write dt, which will just be equal to mu x. Okay, so what I'm essentially saying here is this area underneath here is just mu x, and this area here, since the PDF is increasing, must be greater than mu x. Okay, so then I can deduce from that that qx will be greater than mu x when PDF, I'll just say increasing for lack of space, and the PDF that I'm referring to is the probability density function of the complete future lifetime of a life aged X. Okay, so then when is QX less than mu X? Well, naturally this happens when the PDF is decreasing. Why? Well, it's because I then have a graph that looks something like this. Probably wouldn't look like that, probably look like that. Okay, so from time 0 to time 1, and then this is my PDF here, the TPX mu x plus t, this is my t axis, and at this particular point I have mu x. Okay, so if I draw a constant line there and I integrate mu x from 0 to 1, I just get mu x, and if I integrate this PDF from 0 to 1, I get qx, which will be that area, and that area is smaller than that area, and so I can say this is true when the PDF is decreasing. Okay, so moving on, if I have deferred probabilities of survival or of death, then I write these as such. and this represents the probability that the complete future lifetime lies between n of a life now aged x, lies between n and n plus m. So basically what I'm saying is life currently now aged x, here he will be aged x plus n, and here he will be aged x plus n plus m. I'm interested in the probability that this life dies in this particular time period. So I'm interested in the probability that a life now aged x dies within the next m years once he reaches aged x plus m. So it's just mqx, which would be the probability that the life aged x dies within the next m years. It's that, but just deferred by n years. So I write this extra little bit to say that I must first defer it by n years, and then I calculate that probability. So now it then becomes, this then equals to the probability that a life aged x survives n years, and then times by the probability that a life aged x plus n dies within the next m years. Okay, and there's another proof for this. So this is the intuitive way. Now, we can also arrive at this in other ways. So I'll show you in a moment. So as I said, this was n, the probability that n is less than tx, less than or equal to n plus m. This equals now lx plus n, lx minus lx plus n plus m. Why is that true? Well, out of all the lives that are alive at age x, this is lx, I'm interested in the number that die between age x plus n and age x plus n plus m, which is the difference between those two. Okay, so that represents the probability that I'm interested in, the number that would die there out of the number that are alive there. Okay, now this equals to, if I convert to probability form, this equals to npx times by mqx plus n. Okay, same as what I got there intuitively. Okay, now this, if I write mqx plus n as 1 minus mpx plus n, then I'll get npx minus mpx plus n, but I know that mpx plus n can be written as, sorry, I skipped a step here, that was lazy, so it would be npx times by 1 minus mpx plus n, and then when I distribute this npx, I get this npx out here, and then it's minus mpx plus n times by npx, which just equals to npx minus the probability that life now aged x survives n years and then survives m years, which is just surviving n plus m years. And then this is also equal to, another way to write it, n plus m qx minus nqx. Okay, now the probability that kx is equal to k will be equal to this. Okay, so in terms of notation. So why is that true? Well, I'm looking at the curtate future lifetime being equal to k. So that means this life that's currently aged x, if this is time k, or he's now aged x plus k over here, and here is aged x plus k plus 1, I'm looking at the probability that the curtate future lifetime of this person is k, which means that once he reaches x plus k, he must die within the next year. Okay, why is that true? Okay, so if he were to die over here just before x plus k, he would actually be aged x plus k minus 1. Okay, and he would have survived k minus 1 full years and some portion of a year. Okay, and at that point, then the curtate future lifetime of that person aged x is k minus 1. Okay, so he can't die over there. If he dies over here, then his curtate future lifetime would be k, because any point that's between k and k plus 1, when I floor that number, it becomes k. So that's fine. This area is fine, that area is not fine. Beyond this point, it's k plus 1 and some number. So, and some decimal, and some other whole number. So it could be k plus 10, whatever. The point is that once I floor a number that is greater than k plus 1, the smallest floor that it could be is k plus 1. Okay, so that's not true that the curtate future lifetime will be equal to k then. So he has to die between ages x plus k and x plus k plus 1. Okay, so I did the expectation of the complete future lifetime with an integral. We can also get the expectation of the curtate future lifetime of a life now aged x. Okay, this is equal to the sum to infinity from k equals 0 to infinity, and then that's k times by the PDF, or the PMF rather, sorry, because this is a discrete random variable now, curtate future lifetime, because it's only defined at interval age numbers. Okay, so I don't use a PDF here, I'm using a PMF, and this PMF is going to be equal to this, which is just KQX. Okay, so that's easy enough. Then if I go further and simplify this, I get this to become k equals 1 to infinity kpx, which equals to ex, which roughly equals to e, the complete expected future lifetime, minus a half. So why is that true? Well, let's think about it. I'll give you a little proof, but also let's think about it. If someone's now aged x, and this is their complete future lifetime, so this is now time 0, they're going to die exactly at that point in time. But exactly at that point in time could fall between two age numbers. Okay, and if it does fall between two age numbers, if I'm assuming that deaths are uniformly distributed across each year of age, then I'll assume that that falls in the middle of a year of age, which means that the curtate future lifetime will be whatever this number is minus a half to get to the whole number of this number. Okay, once I've floored this basically. Okay, except it's you don't floor that. So by the way, this does not equal to this. Just want to make that clear. Okay, so what is the proof then? So the proof then is based on the assumption that deaths occur halfway between birthdays. Then I say that kx is equal to tx minus a half. That makes sense. Now if I take the expectation of both sides, since kx and tx are random variables, then I have the expectation of kx is equal to the expectation of tx minus a half, because I can take this half out because the expectation operates linearly. Now this is ex, and this is e with this dot, with this little circle on top, x minus a half. Now this is not actually strictly equal to. The only reason why I'm saying it's strictly equal to is because I've used an assumption. So really, I should be writing this, okay? Because the assumption might not necessarily hold. But if I assume the assumption holds, then I would use a strict equality sign. Okay, now there's some other concepts that I want to go through, and one is uniform distribution of deaths, and the other one is a constant force of mortality. Okay, so bear with me, these are slightly more complicated than the things that we've been doing. Okay, so let's say uniform distribution of deaths. This is going to be a long video, okay. So here I have the PDF TPX mu x plus t. That's the probability density function of a life, of the complete future lifetime of a life now aged x. Okay, so this is the PDF of that random variable. This under uniform distribution of deaths is constant between and where x is an element of integers. Okay, so what I'm basically meaning here is that if someone, so this is an exact age, so x an element of integers means this must sit on someone's birthday. Okay, so they are a whole number of years old. So between that age and the next age, we're assuming that the PDF of their probability of death is constant. Okay, so uniform distribution of death. So it's likely, equally likely that they die at any point in that year is basically what I'm saying. Okay, so what I'm then saying is that their death is distributed uniformly over that year. Okay, so if I say SQX, then this is equal to the integral from 0 to S, where S must lie between 0 and 1. Okay, I'm going to say TPX mu x plus t dt equals to this integral from 0 to S QX dt. And this happens, yes, okay, when S is less than 1, less than or equal to 1. This is going to be equal to S times by QX. Okay, so how did I get from there to there? Okay, well, the way that I got there is, if you look at this PDF being constant between 0 and 1, it's constant. So it doesn't vary with t. So as t varies, the PDF doesn't. It's just constant here. Okay, so that means I can replace this with a constant, and the constant I'm using to replace it with is just QX. Why am I using QX? Well, because if I integrated this from 0 to 1, I would be integrating this constant between 0 and 1. And if I integrate a constant, c, between 0 and 1, I'm just going to get that constant out again. Okay, now the constant that I'm going to pick to use then is just QX, because this is the probability that the person dies within the next year. Okay, so then I replace that with the constant because I'm assuming that probability is the same throughout here. So I can replace it with the constant, and then when I integrate that, it's S times by QX. So note this is not, I'm not writing this as SQX. I haven't just gone full circle back to the same thing. I'm saying now instead that SQX equals to S times by QX when I assume uniform distribution of deaths. Okay, so this is helpful. Why is this helpful? Well, because if I now have T minus X, Q, X plus S, let me write this a bit neater, then I can re-express this in terms of things that I can find on life tables in order to solve for this probability, because I can't just find this probability on a life table. So I now have to assume what happens within an integer year of age in order to calculate this probability. Okay, so that's the benefit of uniform distribution of deaths. And then I could also assume a constant force of mortality or Balducci assumption, some other assumptions about how deaths are distributed in a particular year of age, how this PDF operates in a particular integer of age, so that I can calculate what happens between ages. Now, this is important because life tables, in order for them to be convenient, I have to define them at each year of age. I'm not going to define probabilities on my life table for half a year of age. They're always in terms of a year, so they'll go up in year increments, which means that I don't have any mechanism just from my life table to deal with probabilities that sit within a year or that are not just discrete year things. And I don't want to estimate it, because then I'm going to have calculations that are off, and then I'm going to be setting the wrong premiums or setting the wrong reserves, and I'm going to be making losses as an insurer. So that's obviously not an optimal way to do it. So we have to make assumptions between years of age. And the assumptions that we're making here is uniform distribution of death. Okay, so this equals to 1 minus T minus S P X plus S. The reason I've done that is because I can multiply with the principle of consistency probabilities of survival, but I can't do that with probabilities of death. So in other words, QX T plus S does not equal to QX plus S. Or sorry, let's say Q TQX and then times by QX plus T for S years. This is not true. It would be true if I replaced the Q's with P's, but it's not true for deaths. So I'm going to convert it to P's so that I can calculate this. Okay, so that I can actually multiply them out. Now, how do I want to multiply these out? Okay, well, let's think about it. Let's think about it here. So what am I essentially saying? I'm saying that I have someone that's now aged X plus S, and I'm interested in the probability that they survive for the next T minus S years, which puts them at X plus S plus T minus S, and those S's cancel. So I'm just left with X plus T. Okay, so I want to know the probability that someone survives from X plus S to X plus T. Okay, so in order to do this, I'm actually going to extend the line in this direction first, and I'm going to include this age X here. Okay, so I then go from age X to X plus T. This probability, the probability that someone age X survives for T years, this should be equal to the probability that someone age X survives for S years, and then the probability that someone is aged X plus S survives for this next T minus S years. Okay, and this is exactly what I was looking for. So I can then go and say T minus S P X plus S is equal to TPX over SPX. Okay, so I can replace this with this. So let's do that. I have 1 minus TPX over SPX. And then let me remove all of this. Okay, then if I want to further simplify this, I can go having common denominator, and I'm going to convert this SPX that would sit here into 1 minus SQX, converting it back, and then I would have minus TPX, but I'm going to convert this into 1 minus TQX. Okay, so now, and then I'm also going to convert this denominator into 1 minus SQX. So why have I done this? Why have I converted back now? I've converted back now because this formula holds, where I can take this S out of this subscript here and multiply it by this whole year probability. So I then have 1 minus SQX minus 1 plus T times by QX, and this is divided by 1 minus S times by QX. Okay, and why is this useful? Well, it's useful because S and T are both less than 1 here. Okay, so I don't actually have this probability exactly, so I approximate it with S times by QX if I can assume uniform distribution of deaths. Okay, so then the 1's cancel, and then I'm left with TQX, T times by QX, minus S times by QX divided by 1 minus S times by QX. Now I can take the QX's out as a common factor here, and I get T minus S times by QX. Okay, so this is why uniform distribution of deaths is helpful, is because now I can calculate this with values that I actually have from the life table. If I assume uniform distribution of deaths, I can go through this process. Okay. Now, let's talk about a constant force of mortality. Okay. So now, instead of saying that this probability of death is constant over a year of age, I'm going to assume that the force of mortality is constant over the year of age. So I'm saying mu x plus t will just be equal to mu x, which is a constant, for x, an element of integers, and once again t lying between 0 and 1. Okay, so now t minus s p x plus s, if I want to calculate this similarly to how I calculated this. Now in this case I've calculated the death probability, but it doesn't really matter, I can just do 1 minus and get the other one. So in this case here I'm going to do the survival probability, and this equals to, if we remember our formula from the start, the exponent negative over the time that I'm concerned with, which is s 2 times t. Okay, someone who's aged x plus r dr. Okay, now since this x plus something is constant over this year of age, I don't actually have to write this as a function anymore. I can just replace it with mu x. So I get exponent minus integral from 0 to t mu x dr. And what happens when you integrate a constant is just get the constant out. So you get exponent of minus t minus s times by mu x. And then of course I can just write this as this. Okay, so this is why it's helpful to also assume constant force of mortality. Now it depends on the particular scenario or what the question is asking you to do, whether you must use constant force of mortality or whether you must use a uniform distribution of deaths. Pay attention to what they tell you to do, and then you can calculate things however way you like once you've done that, and you can work between things to calculate different values. Okay, so this is what's going to hold for this probability now. Okay, and now since px would just be equal to e to the minus mu x, now why is that? If I just integrate between 0 and 1, so then this s here is 0 and this t here is 1, then I replace s and t here with 0 and 1 and I just get negative mu x. So since this is true, I can also then say that t minus s p x plus s, this is just an easier way to think about it, is going to be equal to px times by t minus s. Okay. Okay, so sometimes you'll get a probability like that, and now you can just raise this probability to this power. Okay, so what I've done there is essentially, if I replace this, it's just a shortcut to help you think about it. This is not actually like a proof. Okay, so that's another way to think about it. Okay, so right, so let's move on. Going back to our select mortality, if I have Lx plus t, this will be equal to okay, now why is this true? Well, I don't really want to go through the process with you, but it's probably going to take some time. But if we take that across, and then take that across. Let me just do it. Okay, so this is 1 minus q x plus t is equal to Lx plus t plus 1 over Lx plus t. This is the probability that x plus t survives for 1 year, and this just equals to this left hand side. Okay, so that's true. Okay. Alright, and then obviously t here has to be less than the select period so that this probability is actually expressed like this. Otherwise, you might as well just express it as qx plus t, because after the select period, the select mortality is just equal to the ultimate mortality. Okay, so I've already defined what nmqx is, but now I want to know what nmqx plus r is, where x has select mortality. Okay, so this is not actually all that complicated. It's going to be very similar. I'm just going to say now, replace my x with this x plus r from the formula that I wrote for this one. So let's go back to that formula. So this equals to this here, and now all I'm doing is I'm replacing this x with a select life aged x plus r, and all I'm going to do in this formula is replace the x with the x plus r, and then it's going to be exactly the same thing. So don't get stressed out when you see select mortality in a question. It's not actually as complicated as you think. So this is literally just going to be Lx plus r plus n minus Lx plus r plus n plus m all over Lx plus r. Okay, that's exactly the same. You can go rewind and you'll see. Alright, so that's pretty much everything I want to cover for the life table. I know this was an extremely long video, so if all I were to say now is to urge you to actually make sure that you've understood everything I've done here. And I know that I've gone through many formulae. Now just be careful and don't try and rote learn all of these, because it's not actually the way that you'll get good marks in this particular part of the exam. You have to understand everything here and know the basic formulas. Know the basic formulas so you can speed things up, so you're not doing everything from first principles. But all the understanding that I've said in this video, you should understand. And in order to develop this understanding and actually see that you do understand what's going on and are able to answer questions, you need to go practice them. That's extremely important for this section, so you can actually pick up what things you should be memorizing, what things you can take for granted, what things are maybe not so important to memorize to just derive on the spot, that type of thing. Okay, so I'm going to leave it to you now, and yeah, good luck with the studying.